I'm here in the bush, effectively, in the South African Karoo, on a paleontological expedition, and while I have not found many fossils, I have seen lots of interesting wildlife. For example, moments ago, there was an ostrich, a male ostrich, who went charging down this ridge at one of our people, and I got on the radio to warn him that there's an ostrich headed straight for him. And the guy goes up and looks out over there. He doesn't realize the ostrich ran right behind him. I mean, just right behind him. Way bigger than he is. And so that could have ended badly. I've seen kudu and oryx and impala and springbok and not many dangerous animals though. I mean, I ran into a horned adder a couple 3 days ago, but it was no match for these boots. This trip has been very rewarding, but also very challenging, because I just spent the last 10 days in a semi-arid desert that was every bit as dry and hot as some places that I lived in Arizona. Typically like 40 degrees Celsius, and I'm not sure what that is in Fahrenheit. But it's very challenging to be in that all day. So it's extreme conditions. So I am with an extraordinary team of experts in their field as we're exploring Permian strata. And this is not like a classroom place where they would take you to the places where fossils are easy to find. This is where experts go to specifically places where fossils are hard to find. And so that's been a big problem for me, obviously, because I don't have the trained eye that they do. Somehow they've managed to find things wherever we are, and indeed they found things here even, where we were expecting not much to be found at all. And the fossils appear very differently here than they do down in Abrahamskraal, which is it's close to, about a half hour away from Prince Albert. Down there, the fossils tend to be, if they're bone, they tend to be black, and up here they tend to look white, because we're at a different level of strata. And so they're trying to do this for documentation about what appears where in the geologic column and in the stratigraphy, just to show where there's certain index fossils like Diectodon and so forth, where they begin, wherever they go for a poor record. So that's why we're here, because obviously places with green grass and everything would be much harder to find stuff. For me, it's been very, very demanding to be in an environment where there's not just the extreme heat, although the heat alone is enough to drain all of my energy out. And I mean, I used to do this kind of heavy work, where I used to work for laborers, bricklayers. Used to work on construction sites in Dallas. It'd be 115 degrees Fahrenheit and so forth, and I could handle that. But that was 30 years ago, and now we get a call that somebody's found a bone, or that they found a part of a skeleton, and now we would have to get out hammers and chisels and bang away at that for, like, one of them took us 2 days to get this skeleton out of the ground, for all hammering and chiseling and blocking out this area, digging this out, and then separating it from the rock, and then encasing it in plaster and all of that. And it's been an ordeal. And then one of the other fossils that was found was immediately after that. We're all completely bushed and heading back to base camp, and then suddenly we get this call that there was another fossil found up on this hill, miles away, and the closest we can get the four-wheel drives out to this is still like 2 kilometers away, up 2 steep ridges. So that even if we could get the thing out of the ground, we'd then have to everybody gather together on a stretcher and try to carry it straight down a cliff to go straight up the next mountain. And that was at 42 degrees that day. But there was a breeze, so it felt a bit like a sauna. But anyway, I'm going to mix this in with interviews from the guys, and I'm probably not going to be talking a lot more on camera. But this is a pretty place, and I don't get to see places like this very often. So I'm very lucky to be here. We are in the desolate wasteland of South Africa. And I'm with a team of paleontologists and geologists, and I would like all of you to introduce yourselves, beginning with...
Hi, I'm Peter. I'm a postdoctoral researcher at the Royal Veterinary College in the UK, and currently my research project is looking at locomotor biomechanics, so walking and running and things like that, in early dinosaurs and early archosaurs, and seeing how anatomical innovation might have allowed dinosaurs to have gained a competitive advantage against their conspecifics, which might have allowed them to survive and proliferate into the Mesozoic.
So the common ancestor of birds and crocodiles lived about 250 million years ago, and that gave rise to a whole diverse array of reptiles, many of which looked superficially like crocodiles, but were only distantly related to them. One branch gave rise ultimately to the dinosaurs and then the birds, and they're called avometatarsalines or ornithodyrans. And they also include things like the pterosaurs, the flying dinosaurs of the Mesozoic. But as far as the Triassic or the early history of archosaurs is concerned, there was a much greater diversity of animals that are more closely related to modern crocodiles, and we call those the crurutarsins. Or Scutosaurus. And so they include things that looked much like crocodiles but walked with a much more erect limb posture, with their arms and legs held much more vertically beneath the body. And they ranged in size from everything from the size of a house cat through to something the size of a rhino or a hippo, and included both carnivorous and herbivorous forms. And the herbivorous forms actually changed their skull and their dentition quite drastically compared to the other species. Some of them even evolved something like a beak or a snout, something like a pig. They were the atosaurs. Yeah, and they tended also to have very well-developed armour. So a lot of these pseudotsuchian or crocodile line animals had some form of armour on them, so scutes on the back like modern crocodiles. But these atosaurs, these plant-eating animals, because they were so slow being herbivores, they had to develop much more sophisticated sets of armament, and so they developed huge shoulder spines all the way down the back, and they also developed a series of scutes on the belly. So they had essentially a carapace top and bottom of armour to protect them. But you've also got other kinds of pseudotsuchians that looked quite different from modern crocodiles. You've got ones that were bipedal, so things that we call poposauroids or poposaurs. And these superficially looked similar to carnivorous dinosaurs, but at their more detailed bone structure they were quite different. And so some of them were bipedal, some were also herbivorous bipeds at the same time. And
If a crocodilomorph looked superficially like a dinosaur, it would still be plodding on its whole foot, right?
Yes. So the current consensus is that even though they were bipedal, they were probably still plantigrade, although admittedly not a lot of detailed scrutiny or research into that particular question has been done, and it may well turn out that some were digitigrade, walking on their tiptoes, some were more plantigrade and walking on the whole of the foot like we do.
I read that some were arboreal, and that some were high-speed runners.
Yeah, I'm not sure about the arboreal side of things. I mean, small animals can do a lot of different things that large animals can't.
And one with hooves.
Yeah. So there's a whole lot of different kinds of body plans there. There are even sailbacks. So things like Spinosaurus or Dimetrodon, you had an equivalent in the Pseudotsuchians, and they were also poposauroids.
That's going to be a completely different question, but on the subject of sailbacks.
Yeah.
I noticed that, like in the Carboniferous and so on, we have, as you say, you have the Permian Dimetrodon and Adaphosaurus, right? Which are, the sailback on either of these appears to be independent,
Yeah.
right? And then there was an amphibian that had a sailback,
Yeah,
and then the Spinosaurus, which again did not get its sailback from the Dimetrodons because it's a
yeah,
completely different lineage.
yeah.
What was prompting this? Because there's so many. Now you said the Crocodilomorphs had it too.
Yeah, yeah. So the origin of having a sail on your back is quite an interesting question, and there are a diverse array of tetrapods that have, through history, evolved a prominent sailback. And we're not talking about just height-and-neural spines like you see in, for instance, cattle, where it just supports a fatty or a muscular hump on the back. We're talking about something that is clearly sticking way above the rest of the back, forming very much a sail. And so in early tetrapod history in the Permian, you had Edaphosaurus, which was a herbivorous synapsid. You had the coeval Dimetrodon, which was a carnivorous synapsid, and they presumably, based on their phylogenetic relationships, evolved their sails independently. Because Dimetrodon was a sphenacodontid, and Edaphosaurus was an edaphosaur. And so other members of those groups, those respective groups, don't have those sails. And so Dimetrodon and Edaphosaurus evolved their sails independently of one another, but interestingly, in the same time, in the same place. And around about the same time, you've also got an amphibian called Platyhystrix, which also evolves this interesting sail, very much like Dimetrodon. And then later on in history, again in the Triassic period, you've got pseudoseuchian archosaurs. So there's quite a diverse array of archosaurs, like the Poposaur Arizonosaurus. There's also Tenoturiscus, which again they have these very interesting large sails on their backs. And then in the Middle Cretaceous of Morocco and North Africa, you've got Spinosaurus, a theropod dinosaur, which may or may not have been aquatic. The jury's kind of still out on that. And then you've also got a herbivorous ornithopod called Uranosaurus, which again develops this giant sail. And it's very interesting that it doesn't appear that these animals inherited their sails from previous sailback precursors. In each case, they've evolved this same structure independently, originally from scratch. And so it prompts the question: well, what environmental factors would have driven the evolution of this sailback structure?
And part of the mystery of that is that we don't have a single species that does that now.
Exactly. Well, we have sailback lizards of a sort, in the sense that they have a small sail, so extension of their dorsal vertebrae, and sometimes on their caudal vertebrae as well. But these things are that long, and they live in tropical rainforests, things like that. Whereas the paleo environmental interpretation of many of these extinct sailback animals is that they lived in relatively open seasonal environments. And so what is driving the evolution of these impressive sails? And it's interesting to note that throughout the entire history of mammals, the sail really hasn't been evolved, but in reptiles and amphibians. So what one would consider ectothermic or more cold-blooded at that end of the spectrum, they've developed these sails. So there might be a tendency to develop these sails as some way of warming the bloodstream. If you turn the sail facing the sun, it's acting as a radiator to heat up the blood that's passing through that to increase the animal's body temperature. And we find on the surface of the bones of the neural spines that form these sails the impressions of blood vessels. So we know that blood was flowing through these sails, and so even if that wasn't the prime reason for why the sails existed, we certainly know that they would have had, just by the way of physics, that there would have been some radiating function, either to absorb heat or to dissipate it back into the environment.
I'm David. I'm a PhD student at WITS under Bruce and Michael, my supervisors, and I'm looking at sort of mid to late Permian biostratigraphy in the northern parts of the Karoo Basin. So over here we're in the south, where the rock succession is a lot thicker, and up in the north it's much thinner. There's parts that are missing, and so I'm looking at what's happening over there and what animals were around and what the environment was like at the time.
Okay, so basically what I'm looking at is I'm following the ecomorphic contact, which is basically
transition from a marine environment to a terrestrial fluvial environment. And Bruce has basically been following it around from the southern part of the basin all the way up to the north into the Free State, and now I'm basically trying to complete that project and follow it up through the Free States and into KwaZulu-Natal. A big part of it is looking at what were the earliest land animals that we find in that part of the Karoo Basin, because essentially what we were finding is that we have a much older faunal assemblage, which is dated to about 263 million years old, and then we have a much younger one directly overlying it that's probably about 255 million years old. So we have a gap that's in the region of 6 million years. So I was then following that further north to see, can we follow it up further north, and what are the animals, how do they change through time? So basically, first of all, there's several facets to my project. The first one is looking at the biostratigraphy and finding which animals are there, what remains we have. And then the other one is to look at the geology, looking at the environment, and part of that is obviously trying to correlate different rock units and to get an age. So to do that we use detrital zircons, and basically zircons are really hard, robust minerals that form during in a magma chamber or underground in the magma itself, and then they get ejected when there's a volcanic eruption. And so if we can get an ash layer like what we have over here in the Karoo, we can get an absolute age of that eruption. When we get a population that's of a certain age, we can say, well, that's the maximum depositional age. It could be younger than that, but it can't be older than that. Now with the detrital zircons, basically what I would do is I'd come over here to some of these sandstone beds over here and sample the sandstone, and then you crush it, you process it, and you'll extract as many of these little zircons as you can, but you normally want to get between 60 and 100 at least to do detrital zircon dating. And basically what that'll tell you a bit about is the provenance, but essentially the way we do the dating is we will measure different ratios of elements within the crystal. Now when the zircon crystal forms, it'll incorporate uranium into the crystal lattice, but it can't incorporate lead because lead is too light, too small, so it doesn't form inside the crystal. So we know that whatever lead is within the crystal is lead that has resulted or come from the parent uranium isotopes. So we measure two different ratios, which basically are two separate clocks. So we have a uranium 235, which decays to lead 207, and we get uranium 238, which decays to lead 206. So we measure both these ratios, and then we compare the two together, and we can calculate an age because we know at what rate this decay happens. So we can then compare the two together, and then we know, okay, this zircon is pretty good, both ages agree, and so then we can say, well, the age of this is approximately, say, 263 million years old, plus minus. The method I use is LAICPMS, which is basically laser ablation. So you basically ablate a spot, you vaporize a spot of the zircon using a laser, and then that vapor goes into a mass spectrometer, and that's how we read the different isotopes or the amounts of the elements. And then basically that one means that our error bar is a little bit bigger. It's maybe between 2 and 3 million years, whereas the method that Bruce uses for the samples down over here in the Karoo is CA Tim's chemical abrasion, and there they basically dissolve most of the zircon, if not all the zircon, and then they can measure the different constituent elements a lot more precisely, and so then there the error bar is maybe 200,000 years, so it's much more precise. So yeah.
Well, my name is Sifela Nijira. I'm a PhD candidate under the supervision of Professor Bruce Rubich. I'm currently working on a taxonomic revision of a family of Dinocephalians that are currently only known from South Africa.
Right, so why do this taxonomic work? Now, I've been involved in this huge project since 2006 when I joined Wits University. So looking at the biodiversity changes through the Middle Permian. So to do such a project, one has to sort out the taxonomy first, so that you know the true identity of the animals that you are dealing with. So once you have your taxonomy sorted out, then you can now look at the biodiversity changes throughout the rock record. So now these animals that I'm working on, they are found in a biozone called the Tapinocephalus assemblage zone. which is part of the lower Beaufort lithostratigraphic unit called the Abramscral Formation. So now we've discovered that this family only occurs in the upper Abramscral Formation rocks and confined in a lithological unit which is currently known as the Modnas member, with only one specimen we picked from the higher lithological unit of the overlying unit called the Tickle Formation, the lower member known as the Porky member. So that's where the highest record of Titanosuchid dinocephalian comes from. So we have the rest confined in the Modnas member in the upper rocks of the Abramscral Formation.
I'm Frank. I'm a retired geologist interested in evolution and in particular the Permian evolution. We are following a volcanic ash layer to determine the structure. It is an excellent marker, and it has the dual purpose that it has zircons in it which can be age dated by radiometric means.
How many different means do you use? Or could you use?
There are various different ways, but I am no expert on age dating at all.
Okay.
Over here we have two volcanic ash layers separated. We're actually at the moment on the upper layer, which is very well defined, and it has this brown coffee clip at its base. And the other one where they're excavating the fossil is lower. That is an anticline, and we're actually at the moment in a syncline. So it's a syncline which then goes up into an anticline, and this layer is found again closer to the farmhouse. This volcanic ash is very high in silica, upwards of 80%, and it's a very powerful volcano, something similar to Mount St. Helens in the United States. And the ash was put kilometers up into the atmosphere and has traveled several thousands of kilometers to be deposited in the Karoo basin. It is evidence suggests that the volcano was in what is today southern South America when it was still part of the Gondwana landmass and much closer, just off the coast of Namibia. When I retired, I met Bruce at a lecture. I had known Bruce for many years, but I met him at a lecture, and I said to him, one of my bucket lists is to attend a fossil excavation. He said, oh well, there's one in 2 weeks' time, would I like to go? I said, of course. And I went on that one and struggled to recognize fossils the first year, but this is now my 7th one. I love going with them because of the discussions that they have, keeping up with youthful thoughts because of all the young doctoral and postdoctoral students, and to be with nature, and in particular in this harsh environment where life really shows you that it has the urge to keep going.
I'm Mark. I'm a PhD student at the University of Witwatersrand, also under Bruce Rubich. Just about 2 weeks away from finishing the final corrections. And I study Middle Permian pariasaurs, like big Russian taxa Scutosaurus. Oran, so we just found this small Dicynodont skull over here. And let me turn it around for you. Okay, so this is looking from underneath. So this is the lower jaw, this V-shaped structure here. It's the bottom of the lower jaw. And then we have 2 canine teeth sticking out either side there. So those are the canines, the only teeth these animals have. It's probably Diectodon, which is a very common Karoo fossil that we find, little plant eater with a tortoise-like beak. And if we turn it over this way, the nostrils would be here, eyes and the jaw muscles in the back of the skull. So unfortunately, it's sheared off sort of straight through the line there. But this is how we find them. This was loose right here on the ground. I think it was over there, like that. So when we walk around, we go for these kind of green-grey outcrops. That's the mudstone or siltstone. We're literally old mud that buried the skulls. And they erode out of the hills and then look like that. So not a very good skull, but it's a start. It's very early still, not even 8 o'clock yet. And yeah, we'll keep searching for more and heading to the house that way.
I'm Kevin. I'm a postdoctoral fellow working on geochemistry, trying to understand climate change and ecology of Therapsid and all the tetrapods from South Africa in a Permo-Triassic. So I study geochemistry, so basically I look at the isotope inside the bone, because every atom they have several kind of states and the ratio is dependent of several parameters. So I'm studying oxygen, because oxygen is regulated by parameters like environment temperature and body temperature. So I can look at either one of them to be able to reconstruct paleoclimate. Like what I did during my PhD was to try to reconstruct the variation of temperature from Middle Permian to Middle Triassic, and we managed to see that during the end Permian mass extinction, the most violent one, we got a huge increase of temperature, a huge climate change that induced a huge catastrophic event in the biodiversity.
I'm Julien Benoit. I'm a senior researcher at the University of the Witwatersrand Evolutionary Studies Institute. I look at paleoneurology in therapsids, which means I use X-ray imaging to look inside the fossilized skull, in order to see the nerves and all the sense organs. So the idea is to reconstruct what did therapsids could smell, see, hear, and feel in general through the neurological structures. So I look at the paleoneurology of therapsids, which is I look at the evolution of the sensory organs in the ancestor of mammals, and for this I use X-ray and synchrotron tomography, which is just a very advanced way of saying that we are doing like medical imaging, but more powerful to look through the fossilized bone. And through the paleoneurology, what I want to look at is the evolution of the brain, specifically the evolution of the sensory organs, like the inner ear, and more particularly also the trigeminal nerve, which is the nerve that innervates the face in mammals. And in mammals it's a very important nerve because it innervates the whiskers. And what we find out is that most of the therapsids don't have whiskers, actually don't have a trigeminal nerve that corresponds to the one we can see in modern mammals today. But we can find some of them, among the most derived of them, which are called the cynodonts, that do have a trigeminal nerve morphology that reflects the presence of whiskers. And this is very important to us because it means that they had hair, and hair is the main proxy to reconstruct the evolution of endothermy. It's the main correlate to endothermy. Endothermy, it's simply stated, it's warm-bloodedness. So warm-bloodedness is the fact that you have warm blood. So mammals, modern mammals do have warm blood, and we know that they evolved from animals like reptiles that do not have warm blood, that have cold blood. And we want to know when this happened. And to do that, we looked at different aspects of their paleobiology. One of them is the isotopes. Some other people look at histology, and I look at the neurology to see where the hairs evolved. So the trigeminal nerve gives us off the evolution of whiskers, and whiskers being hairs, it also said that they had the genetic material inside the DNA to make hairs.
I'm Mike, and I'm a curator of fossil vertebrates at the Natural History Museum in London. And my research focuses on the biostratigraphy of the Middle Permian part of the Karoo in South Africa, sort of diversity change from the Middle Permian into the Late Permian, and the sort of diversity loss associated with the Capetanian mass extinction.
So here we are out in the field. So this is where we've been collecting, sort of in the area below this mountain over here. So what I'm doing now is trying to measure a stratigraphic section. So we're trying to establish where these rock horizons come through, and to work out where to start measuring and where to end measuring, so we can plot the fossil localities onto the rock section. It can be quite difficult, and it is quite difficult in this area because there's a fair bit of folding. So this morning we've been sort of tracing out quite distinctive marker horizons. So one was this sort of tufaceous layer with sort of calcareous, a thick calcareous layer right on top of it, or actually sometimes below it, in close association anyway. And so that sort of occurs coming through here. And now we've got it on this side of the mountain, so we're just looking at how the stratigraphy on that side of the mountain relates to this side of the mountain, and that will give us the sort of the context. Then we can plot our fossils and our tufaceous horizons onto that.
My name is Bruce Rubich. I'm the director of the Centre of Excellence for Paleo Sciences in South Africa, and my interest is in therapsids, basically Karoo vertebrates in broad terms, but I have a particular interest in using fossils to understand biodiversity change, and also to use that information to understand basin development and Gondwana distribution of organisms in the Permian particularly.
Okay, where we're standing now is very close to where I started my field work 40 years ago, and it's really gone full circle, because on that field trip I found this new species of Dinoco called Tapinocaninus, which I eventually named, and now on this field trip we found another specimen of Tapinocaninus, and so it shows that we're back at the same stratigraphic horizon that we were at 40 years ago. But in the meantime we've achieved a whole lot. We've gone upwards in the stratigraphy from rocks that are about 266 million years ago up until 260 million years ago, and we've recognized that at 260 million years ago we've got a major extinction event that happened at the end of the Capetanian period, and it appears that from the Karoo record, which is really the only good record of biodiversity in the terrestrial realm of land-living animals of that period, it appears that we've got about an 80% extinction at that time. So I think that's a huge contribution, and given a big understanding of what's going on, because that extinction has been picked up in the marine realm in China, and where it's been dated at about 260 million years, and we've got a very firm date of 260 million years from here in the Karoo in South Africa. And what is important about it is we've been able to document the changes in biodiversity that have taken place through that period from 266 million years ago to 260 million years ago. So as we've gone into the younger and younger faunas, we've been able to see which animals come in and which disappear. And what we've been able to do is what was one big zone in the past, we've now been able to subdivide into 3 different zones. And hopefully we'll be able to correlate these with other sequences around the world.
I don't know that anybody in my audience will understand any of your introductions.
It sounds impressive.
Okay, so I just see if there's any kind of consensus here. What motivated any of you or all of you to hold the position, the interests that you do?
I've always had a deep interest in paleontology because I grew up in the area. I grew up in this sort of landscape, and there are lots of fossils here. My grandfather had a particular interest in collecting fossils, and it was his hobby, and I guess I inherited that, and then I went on and studied in that direction, and I was I've just been very fortunate. I've landed in the right pond, and I've enjoyed swimming around and collecting fossils in the Karoo and understanding biodiversity change.
Okay. And full disclosure, I asked this group this question earlier, and everybody said Jurassic Park. If anybody would like to throw out a different answer, like Bruce did, we don't have to go in line or anything. Just does anybody have anything?
Well, for me, it was kind of also growing up. My dad's a geologist, so he found a bunch of fossils when he was doing his stuff. So I grew up with fossils. My mom also had an interest in fossils. She went to Wits to the then Bernard Price Institute when she was about 10. Her dad took her to meet James Kitching, and he showed her a bunch of bones, and she was interested in that. And then later she was working at Golden Gate, where he found the Massospondylus eggs. So I grew up with fossils, but I didn't really consider it a career until about 2012, when my mom took me to a conference down in Cape Town, and there I met Bruce and Mike and a bunch of other guys and got to chatting, and then it was like, oh, okay, maybe this is something that I should look at studying further once I'm done with my undergrad degree. And here I am.
Anybody want to throw out why their work is important, or why this field is important?
This work is important because there's, particularly in understanding mammalian origins, there's an unsurpassed record of therapsids in this country. It's probably the vertebrate group that best documents the evolutionary development of one form into another. In other words, from basal tetrapods through to mammals, and you can follow it through the whole Karoo stratigraphy. So the Karoo stratigraphic sequence in the world is an icon for world paleontology. It gives us an understanding of how one form developed, one type of form gives rise to other forms through time, and so traces the evolution of species through time.
Okay, so everyone gathered around this table, aside myself, of course, are all notable scholars in your field. And I just want to bring up that there was a senator in Tennessee who said last week that there is no solid proof that the Earth is millions of years old. What would you say to him?
Wake up.
Well, I think that there's a lot of proof that we've got very good dating techniques, and there's a lot of proof that the world is billions of years old. That's from very good dating techniques, and I'd like to answer what we're doing over here that proves that point as well.
Well, we're fortunate in the Permian part of the Karoo here to have layers of sort of volcanic ash, sort of tufaceous horizons, and they contain within them mineral grains, primary mineral grains, which we can use for dating the age of those rocks. So the minerals form at the time that magma cools and then are ejected from the volcano, and there's certain ratios of elements that fit in those crystals at that time, and some of them are radioactive and they decay at a known rate. And so we're looking then at ratios of the parent isotope of certain elements to daughter isotopes of different elements to which they decay. We can work out the amount of time that has passed since that grain was formed, and that allows us to date the age of that mineral, and by extension the age that horizon was deposited. And that's very useful here, and by getting sort of good samples, a number of grains that have a similar age, and the youngest population thereof, we sort of can work out the age of that horizon, and then we can look at the spacing of those horizons throughout the sequence, and look at sort of the passage of time and how much time is represented in those rocks, and that provides a framework onto which we can place the evolution of the animals that are preserved in those rocks.
And we've had great success in this part of the Karoo Basin on that. So we've got for the oldest Beaufort group rocks at about 266 million years, and going up to 260 million years for this big extinction. And the nice part is when we send our samples away for analysis, they come back in the right stratigraphic order, the oldest at the bottom and the youngest on the top. And so that's no coincidence, that is because it is like that. oldest rocks. Bottom, the youngest rocks.
So the fossils. So what's important there, I think, is that so very often there is the mistaken assumption that we use the fossils for dating. We use the fossils to correlate and maybe order the sequence of of different stratigraphic horizons that we already know follow each other. So the fossils are there to confirm the stratigraphic order, or we use them to confirm the stratigraphic order. But the dating that Mike talked about is completely independent. So as Bruce said, it could come back in a completely random fashion, and it does not. Like the dating could come back with dates that do not follow each other or that are completely random. They do not. They are perfectly ordered in the stratigraphic sequence and confirm that what we say from the fossils and from the lithology is consistent.
So what you're saying is you use the index fossils for relative dating to show which strata is older or younger than which other strata, but the actual dates in terms of numbers of years come from radiometric dating, and those are absolute.
Yes. Yeah.
Exactly.
And we use an independent dating laboratory to do that for us. In fact, it's MIT in the States.
And you never get a sequence, you never get a strata that is in the wrong age, or that it's too young to be. The date shows that it's too young to be in that order. That never happens.
We haven't had that yet. I can guess that things could go wrong in the laboratory also, but we have never had a date coming out in the wrong succession yet.
Well, with the radiometric dating, there is a phenomenon known as lead loss. So it can be that with less accurate techniques, if you get the loss of one of those daughter isotopes, the ratio between these two isotopes shifts a bit, and so it can give ages that don't quite make sense. The technique that we use uses chemical abrasion and then thermal ionization spectrometry, and that has shown consistency.
But you're not using carbon dating, are you?
No, carbon dating wouldn't be very useful.
Why would carbon dating not be very useful?
The half-life of
carbon 14.
Yeah, is it carbon
12
14?
to 14.
Isotope, yeah, is much too short. So it decays to sort of levels that are negligible and cannot really be detected. I think it only is effective up to 40,000 years or something.
So if it's only 40,000 years, then carbon dating would only be used for archaeology and not for paleontology. But I've noticed that the people in my country can't seem to distinguish archaeology from paleontology. They kind of think they're the same thing. So there are, as I understand it, a couple dozen maybe, or at least a dozen different radiometric means of dating. Is that right?
Yeah.
Okay, and then
it's not my speciality at all, but there are other methods that are not radiometric, and the interesting part is that when you date these different rocks, you get similar dates from different types of dating, so they can't be too far off.
But that's important when you overlap all the different means of radiometric dating, and then plus barbs and ice cores and all of the other, and dendrochronology and all of the other non-radiometric data, you still get an overlap.
Yeah.
Where they all sync.
Yeah. And it's getting better. 10 years ago it wasn't as developed as what it is now. All these techniques are developing all the time and getting better and better, and we're getting, I think, quite good resolution on these rocks.
One of the things that impresses me when watching you guys in the field is how you can immediately recognize when you find a fossil, you can recognize from the little idiosyncrasies or whatever what is the word, the particularities of different fossil bones or whatever, you recognize that this is consistent with this taxonomic class, and this or it's indicative of this other I mean, it doesn't specify which species, but it does give you the general range. And it's interesting that you guys know this and can tell it, because there's a lot of people that would say, well, you just found a bone, that doesn't mean anything. That only means that it died.
I think in this context over here, all of these people are specialists in their field. And they're all doing doctorate degrees on a particular type of animal, and they are the world specialists on those particular animals. Mark has just finished his doctorate now 2 weeks ago, and he's been working on this group of animals, large animals the size of this table, 3 meters body length, and standing higher than a sheep. and he is now the world expert on bryosaurs. So he's able to identify a species from relatively small.
And we were all talking about species from the Permian, or before the dinosaurs.
Indeed. And I think that Mark's group is an interesting group, and maybe he'd like to elaborate on that, because that group made it through one extinction event and then didn't make it through another extinction event. Maybe he'd like to talk about that.
Yeah, okay, thanks, Bruce. So Bruce is talking about pariasaurs, and the most common one that people know out there is probably the big Russian pariasaur Scutosaurus, which was in that BBC 2001 series, Walking with Monsters and Walking with Beasts. So there are about 20 species all over the world, only Middle Permian and Late Permian, and went extinct at the end of the end of the Permian. And in South Africa, we've got the highest number of different species of any region in the world. So about half of all the species in the world are in South Africa or Southern Africa. So because I'm part of Bruce's lab at the university, we study the Middle Permian, which are the first pariasaurs to occur. So they are here, they appear quite abruptly. They're all very large animals. They're also very similar. It's hard to distinguish them sometimes. And they go extinct at the end of the Middle Permian, the Guadalupean Capitania. And then after that time, we have a new fauna arising from elsewhere, which are mostly medium and small sized pariasaurs. And also those are in a lot in Russia and China and that part of the world. But at this time, these are some of the most abundant herbivores out there, some of the most abundant plant eaters. They're very stocky built, sort of hippopotamus style animals, very thick, very stocky, not galloping runners or anything like that. And they have big cheek frills on the side of the skulls, so they look superficially like a Triceratops, which has a frill behind its head. And they have scutes and things on the back, like crocodiles do, bony plates in their skin.
Well, you just brought up something. You said you're hippopotamus-like, and a lot of people in my country will think that you just said it's a hippopotamus. So can you get what implying that it is at least a mammal? So and this is an important thing to bring up. How is it not a mammal?
No, so at this time there are roughly three kinds of groups of major reptiles. We have the reptiles that are going to become mammals, which we can call mammal-like reptiles or therapsids. We have archosaurs, which become crocodiles, dinosaurs, and birds. And then we have a third group called parareptiles, which is a bit of a wastebasket taxon with where we put in the other reptiles that don't really make sense. And also includes animals we used to call anapsids, which means they only have one hole, they have no hole behind the eye. So those are the three.
Your pariasaurs?
Yeah, and that includes pariasaurs and other miscellaneous taxa.
So if I'm hearing you correctly, you said that you have what we would traditionally call reptiles, and I know some people will balk at that and say synapsids were never reptiles, but whatever. I know some people will get persnickety. You're talking about what traditionally we called reptile becoming mammal, and all of these animals that we're talking about, excluding the pariasaurs and the archosaurs, all of these others, the therapsids, these are in a state of transition between reptile and mammal in that traditional sense, right?
That's right.
So you're saying you have transitional species?
Yeah, well, in one sense, every species is transitional. But just to finish what we were saying, the reason I said hippopotamus-like is just, I was talking about their lifestyle. So they were probably close to the river edge, maybe in swampy lands. We find them preserved as complete skeletons very often, standing upright. So stuck in the mud is a phrase that was attached to them 100 years ago. So these are maybe semi-aquatic animals, although Kevin's done some work on their lifestyle as well. So when we say something like hippopotamus-like, we talking about the size or the lifestyle or the ecology.
Okay. For your identification question, so you here in the Karoo we have a record of the continental landscape in the Permian. So we have tetrapods mostly, the amphibians, and then the two groups of amniotes, the reptiles, so the sauropsids, and the mammal-like reptiles, the synapsids. And the identification is quite straightforward. The amphibians, they have that ornamented pitted skull, very flat and rounded snout, so they are quite easy to identify. The synapsids always have a canine, and that's a trait that we kept from those synapsid ancestors, because mammals are technically considered synapsids, and therapsids are also considered synapsids. And then the reptiles are those with that have the teeth are all the same, and then inside the reptiles you would have your parasaurs that have leaf-shaped teeth, but consistently the teeth are all the same size. There's no canine, there's no incisors, there's no molars. Yeah. And then inside the synapsids, and now I'm going to your question about the transitional species. So here in the Karoo, what is fantastic about the Karoo, and as a ornithologist trained in Europe, I can say that the quality of the fossil record in the Karoo is legend. It's as Bruce said, it's iconic. It's one of the top best sites in the world, very comparable to the Hell Creek in the United States. It's sequence upon sequence of fossil record, and you can easily follow the transformations of the species through that record, because except in that direction where the things are tilted, but in that direction, which is most of the basin, the layers are mostly flat. And you can really, like from Beaufort West, for instance, you look at that cliff that you saw earlier, and you can really see those layers, and those layers represent 10 millions of years, and you follow the evolution of species through those millions of years. And among the synapsids, you have first the synapsids that are represented in Texas, the earliest one, the pelicosaurs, that have a canine, but it's not very well developed, and very often you have more than one caniniform. And then you go to the therapsids that have a very well-formed canine, and they have the temporal fenestra that is very well developed, unlike the pelicosaurs. So the transformation goes on to the mammalian stage, when you have a canine, definite molars, definite incisors, and the temporal fenestra is so big that you have a sagittal crest. So we humans are an exception among the mammals, because we don't have a sagittal crest anymore, but if you think about gorillas, chimpanzees, they do have a sagittal crest. So that's a trait of mammals, and you can follow that transformation through the fossil record. And you have also the transformation of the lower jaw bones into the middle ear bones. So we mammals have only one bone in the jaw, which is called the dentary bone. And if you look at the pelicosaurs, so the North American early Permian synapsids, they have up to 7-8 bones in their lower jaw. So it's a lower jaw bone that looks very much like that of modern reptiles, and that's why they are called the mammal-like reptiles. That's the reptilian trait in the mammal-like reptile name. And then these jaw bones are pushed back in the evolution by the dentary that develops backward. And same thing, you look in the Karoo, you start from the bottom to the top, and you find species upon species that have more and more developed dentary, until you reach the point which is the Diarthrognathus. Diarthrognathus is a cynodont, so it's one of those, it's the group of the mammal-like reptile that is the most directly ancestral to mammals. And in Diarthrognathus, you find a jaw that is completely made by the dentary, and the post-dentary bone, so the future middle ear bones that are attached to the top of that dentary, almost in the position that you find them in mammals. And what's interesting with that, the Diarthrognathus, is that it has the articulation of the lower jaw. So let's start from the beginning. Diarthrognathus means D is for two, arthro is for articulation, and gnathus is for the jaw. So it's the jaw with two articulations. Why do we call it that way? It's because mammals are distinguished from reptiles by that lower jaw articulation. Mammals have a lower jaw articulation made with the dentary, so the single big bone in the lower jaw. Reptiles have an articulation of the lower jaw that is made by the articular. So the skull articulates with the lower jaw via a bone, an intercalate bone called the articular. That's the reptilian situation. And Diarthrognathus has the two. it has the mammalian jaw articulation, it has the reptilian jaw articulation. That's what it's called, Diarthropnatus. And it's because the dentary has developed like in mammal, but the jawbone is still attached to the lower jaw like a reptile. So it's a perfect missing link between the reptilian condition and the mammalian condition. You have the two conditions in the same species.
Practically none of my countrymen are going to understand that, even with subtitles.
So that sort of transition occurred in the Triassic-Jurassic transition, but we over here in the middle Permian, and I think that Cephalani is working on a very interesting group of animals called Dinocophalians. They're animals which have got very large, they're large animals, they're the first really large animals to have lived on land, living tetrapods, and the group that he's working on, the Triceratops, are found only in South Africa. Dinocophalians generally are found in South Africa, in Russia, South America, and in some African countries. The Triceratops are only found in South Africa, and maybe Cephalani can tell us a little bit about what he's looking at in these animals.
Yes, please.
Okay, yeah, so work on these animals was done in 1969 by a guy called Leo Boomstra. So, having looked at this group or this family, we came to a conclusion that it's composed of 2 genera and 9 species. So having looked at all this material, I'm now quite convinced that yes, of course, we have 2 genera, but not 9 species. We have only 2 species, based on the morphology of the universe.
So I think that's important work because it helps us understand the biodiversity change. How many species are there actually? You know, in the past when people described forms, they might have worked on imperfect skulls and skeletons and not always understood the diversity in form that occurs, or the diversity, the amount of change in different bones that can occur within a species. Now Cephalani's gone and done a re-look at all the specimens known and has come to the conclusion that there are 2 species present of this family, of this original 9 species. So that's why it's very significant work. But another very piece of very significant work is what Kevin's doing. He's looking at isotopes, and I think it's best if he explains what he's doing because otherwise I'll take the words out of his mouth.
Okay. So isotopes, like atoms, they have different kind of states. So you get different weights basically, but for oxygen you have like 3 of them, carbon also. Some are stable, some are radioactive. So I'm looking at the stable one. So basically you can find them everywhere in the environment in different proportion known. And for oxygen, I'm looking at oxygen mostly. It's present in water, of course, and when the animals are drinking the water, this oxygen is like incorporated into the bone and the teeth. And as it is stable, the ratio of oxygen, different oxygen, are gonna stay in the fossil even in millions of years. And this ratio depends on several parameters. And if you know the parameters, you can go back to them and interpret them. So those parameters for oxygen are the environmental temperature as well as the metabolic system of the animal. So in fine, you can go back to what was the climate temperature at the time of the animal drinking the water, and also you can go back at the body temperature of the animal with the oxygen. So basically what I did in the middle Permian, even late Permian, is like trying to reconstruct the variation of temperature through time and to see what happened when the temperature change associated with the mass extinction. So here it allowed us during my PhD to show that the Permian Triassic mass extinction, which is like the most important mass extinction in all time, is correlated on continent as well as in the ocean with a fast, huge increase of the temperature. So climate change is a thing, and we can see in the past we have records that when the temperature increase, we have a loss of diversity and a lot of species die because of that.
So you're saying climate change is the thing, and it's dangerous.
Yes.
Okay. All right. So, would anybody else would like to contribute?
And I think that David, he's not looking at climate change, but he's looking at environmental change. He's following the shoreline around the Karoo Basin and looking at which types of animals occur on that shoreline, and maybe he can just enlighten us a little bit about that, the work that he's been doing and how he does it.
So basically, I've been following the shoreline contact, which is a transition from a marine environment to a terrestrial river land environment, and looking at what animals are occurring just above that contact in the northern parts of the basin, because it hasn't been studied as much as in the south. And what we found is sort of in the southern Free State, just north of the Orange River, we have a fauna that is very similar to what we're expecting to find down here, much older, about 263 million year old fauna dominated by Eucymops, a small dicynodonts, and Glanosuchus, which is a big meat eater, a bit like a lion. And then above that we have a much younger fauna, which is more similar to what happened to the one you get just before the Permo-Triassic boundary, so Dactycephalus zone fossils. And so basically we have a gap between the two of about 6 million years. And so now part of my PhD is looking at, well, how can you explain that gap, and what does it mean in terms of basin development with the Cape Fold Mountains that are to the south of the study area basically being pushed up. How does that affect the size of the basin and accommodation space? Because in the north we're picking up that there's these gaps, these pieces of missing time, which we see in the south but are missing in the north. And that is quite important in terms of understanding just basin dynamics and how did the basin actually develop during the mid to late Permian.
So you see, in order to do, this is a very big study, and in order to do it you need different expertise from different people with geological expertise, isotope expertise on the animals, and Julian has been looking particularly at the brain and the neurology of therapsids. He's really a leader in that field because he's one of the first people to have ventured in that thing, and I think that he's come up with some interesting conclusions which maybe he'd like to tell us about.
Thank you. So as I was saying earlier, you can follow the transition from the basal pelycosaurs to the cynodont, which are the most mammal-like of the mammal-like reptiles, through the Karoo and through the fossil record. And one of the big questions we want to answer about those therapsids, the evolution of therapsids, is when did they develop the mammalian characteristics, particularly hair, mammary glands, and other sensory adaptations that mammals have, like their capacity to hear high frequencies. And this you can do by looking at CT scans, so using X-rays, like the X-rays you use at the hospital. That's the exact same principle. So you look inside the fossil through X-rays, and you can see the fossilized nervous structures of those mammal-like reptiles. And what is very fascinating is that you can follow the evolution of a particular nerve called the trigeminal nerve, which is the nerve that innervates the face and the whiskers particularly. And you can see that nerve transforming from its reptilian condition to the mammalian condition, which are very different. I'm not going to the technicalities of that, but the two conditions are very different, and you can see that transformation. It's very smooth, very gradual, and we think that at some point, like 240...
So what he's saying is in the younger rocks, you can see how this change takes place. So from the older through to the younger rocks. And that's why the Karoo is so fantastic. But he'll continue now, because I think it's a wonderful story.
Yeah, I think I need subtitles.
Yeah.
So the dubbed version of French South African evolution of therapsids. So you see that transformation of the trigeminal nerve. And once again, to answer your senator, if there was no evolution, there will not be that kind of transformation. There would be inconsistencies all over the place. It would be completely random. It's not. We have before 241 million years, you have the reptilian condition, and after 241 million years, you see the mammalian condition starting to evolve. And this indicates that maybe somewhere in the Triassic, 240 million years old, it's about the Triassic, and it means that there the mammals started developing hairs, because they started developing whiskers, and whiskers are essentially hairs, which connects to the evolution of warm-bloodedness that Kevin studied through isotopes, and he gets quite also a consistent result with this, with the mammals, the mammal-like reptiles developing endothermy around the Triassic also. And it's also consistent with another trait, which is the loss of the pineal foramen. So some reptiles today, like the Komodo dragon, for example, there is iguanas, the tuatara, the New Zealand weird little lizard, they have a third eye on the top of the skull, which is called the pineal eye. And this pineal eye is housed in a foramen called the pineal foramen. So it's a hole in the skull, literally. And mammal-like reptiles used to have that. We see that from the pelycosaurs in North America in the early Permian. We see the pineal eye in the late Permian in the reptiles, in the mammal-like reptiles that we have in the Karoo. And then again, 240 million years ago, in the Triassic, it's lost. So the pineal foramen is lost, not suddenly, it's gradually lost in 240 million years ago in the cynodonts. So, and we know that only ectothermic, so cold-blooded species today have a pineal foramen. Warm-blooded species don't have a pineal foramen. So that means that the transition from cold-bloodedness to warm-bloodedness also happened in the same times as they were evolving fur. And from genetic data, we know that the closing of the pineal foramen, so the loss of that hole at the top of the skull, is genetically connected to the capacity of secreting milk. It's a very weird, one of those very weird genetic connection. It's a gene called MSX2 that controls that, and it's somehow directly correlated to the closing of the pineal foramen. So we have a very consistent signal that supports that mammal-like reptiles evolved their mammalness 240 million years ago. The lactation, hairs, and endothermy, so warm-bloodedness. So and again, this is all documented by Karoo species, and once again, you will not find that kind of very consistent signal through time and stratigraphy if there was no evolution ongoing.
Now, I think Frank wanted to make the point that because all these continents were linked once upon a time, we get distribution of these animals in different continents. Maybe you want to expand on that?
No.
The point is that the continents were joined. So what happened in America is part of the continuum that we see here in South Africa, or in Russia, or in China, and so on.
It's all a matter of where sediment is accumulating and where fossils are preserved.
And Peter?
Sure. So in my current line of work, I study dinosaurs and archosaurs and things like that, early crocodile relatives, and how they walk, or they could have walked, or how they could have run, or things like that. But biomechanics, which is basically the application of the principles of physics and engineering to answering questions in biology. Biomechanics also has a really interesting take on the evolution of mammals from reptiles, and again, which is documented very, very excellently with the Karoo fossils. And in the context of my work, which is locomotion, the Karoo fossils help document this remarkable transition from how animals move like reptiles today, which is very sprawled posture where the backbone moves from side to side, so very much like a lizard. And they transition from that kind of locomotor behaviour through to something that's very much more mammalian, where the limbs are held much more underneath the body, so like a cat or a dog or a horse, and the backbone moves in a novel fashion during high-speed locomotion, so it moves up and down. So if you think of a cheetah or a racehorse when they're galloping, the backbone is flexing up and down. And that is, from a physical or a mechanics perspective, not an easy transition to accomplish. You don't just go from sprawling to upright overnight. It's a very difficult physical problem, and yet it was overcome by the ancestors of mammals. And so the fossils of the Karoo, as we study them through time, we can start to understand how you can actually go from one mode of locomotion to another. And so by applying the principles of physics and engineering, looking at the structure of the bones, how they articulated, looking at the surface of the bones, which tells us where individual muscles attached, so that we can then infer from that the direction in which muscles pulled on the bones to move them. We can start to reconstruct how these animals stood, how they moved, how fast they were able to move, how high they could jump, things like that. And so when you put this engineering perspective onto these fossils and then put that into the context of millions of years of gradual change, you can start to gain a really deep understanding of a major functional transition in the fossil record, changing from animals to reptiles. And so, from my interest, I'm about locomotion and limbs, but there's also another major transformation which Julian hinted at earlier, which is the evolution of chewing and the evolution of jaw function. And so reptiles, they have, in association with a different structure of the jaw and structure of the skull, reptiles very much have a much more simple mode of processing their food. It's basically just moving the lower jaw up and down to coarsely, crudely acquire and process their food before swallowing it. Whereas mammals today, in association with a wide variety of complex tooth shapes, they can chew their food. They have different shaped teeth for different purposes, so in sizes and canines and molars and things like that. And that's also associated with a rearrangement of the structure of the jaw joint and a rearrangement of the muscles that run from the back of the skull to the jaw to actually move the jaw. And so by studying, again, the structure of the bones, understanding where the muscles attached, how big they were, how they pulled on the bones, we can again understand another transition from how basically a reptile-like mode of food acquisition and processing evolved into the highly sophisticated manner of food acquisition and processing that we see in mammals today.
Previously we had Peter Bishop was on the team from Australia, and he's gone on to another project. And replacing him at the same day was Victor. Now, you're from the University of the Witwatersrand in Johannesburg.
Yep.
Victor, what is it that you do?
I work on a group of less cool animals called dinosaurs, and so much younger rocks than what we're looking at right now. So right now the rocks we're looking at are from the Permian. I work on rocks from the Mesozoic and particularly the early Jurassic and early Cretaceous.
So what are you doing here?
Apparently,
there's no dinosaurs.
What?
That's one of the things I find fascinating about this. We're walking around in strata that we know, and so we know what we're going to find before we find it, and we know what we're not going to find. Somebody made the joke about, well, could it be a hominid bone? Yeah, that would certainly disrupt all of our careers. If there was a hominid in the Permian.
It would really change the way we optimize phylogenetic trees, and it would produce a crazy ghost lineage. But it doesn't falsify evolution entirely.
Okay, so tell me more about your specialty.
Yeah, so I work in phylogenetics, and I also work in a little bit of paleobiology as well. Paleobiologically,
phylogenetics, what's that?
Phylogenetics, sorry, my bad. So I study the family trees of a particular group of dinosaurs within theropods called Coelurosaurs. So coelurosaurs include everything from Tyrannosaurus rex and birds and everything in between. It's been quite an innovative point in theropod evolution. And looking at that particular point in theropod evolutionary history, that's when things start to get a little bit weird with theropods. Theropods start experimenting with the way that they elaborate their feathers, and they start exploring new niches, and they really start deviating from the hypercarnivorous primitive condition and really start experimenting with herbivory and insectivory and potentially filter feeding as well.
Are you talking about therizinosaurs?
So therizinosaurs are herbivorous, Oviraptorosaurs as well, ornithomimosaurs are herbivorous as well, and then these little things called alvarezsaurs, which are things like Mononychus, tiny little guys with a single digit. They would scratch into insect nests and lap up insects. They're kind of like a jerboa crossed with an anteater. They're kind of cool.
Are you sure about the Mononychus use their claw that way? Because, you know, emus have that single digit as well.
Yeah.
But they can't do shit with it.
Yeah, they can't. But, I mean, if you look at the rest of Mononychus and this other thing called Shibuya, if you look at their forelimbs, they really are very robust. They've got an extremely big protuberance on the back of the ulna called an olecranon process, and that triceps muscle attached there, and that's responsible for digging and for this sort of motion. Their claws also face a particular way, and there's only one thing, if you have the arm of Shibuya or Mononychus, there's only one thing you can kind of do with it. They weren't burrowing, but they were likely scratching into nests or something like that. That's the working hypothesis. They also have a really reduced skull, the reduced dentition, very weak skull, and we see that happen in mammals that become insectivores. They also reduce their teeth and eventually lose them. So, and that happens in multiple lineages independently. But as far as coelurosaurs go, I'm studying a South African coelurosaur, currently the only coelurosaur in Africa, called Inglabersaurus. So Inglabersaurus was discovered in the late 90s, described in the early 2000s. And then I scanned it at a synchrotron, which is like a big particle accelerator that produces high-powered X-rays. I scanned that and I reconstructed the bones digitally. And I've now coded those bones into a phylogenetic matrix to see where it sits in the theropod family tree. Previously, it was at the base of ornithomimosaurs. That might change. Yeah, keep an eye out for that paper. Shameless self-promotion. Okay. All right. And then the paleobiological side of things, I work on a group of dinosaurs called ornithischians, and that includes things like Stegosaurus, Triceratops, duckbill dinosaurs, and Scutosaurus, all the really cool, spiky, badass dinosaurs. They're my guys. And I'm working on a new specimen of Heterodontosaurus that shows how those group of dinosaurs were breathing. So ornithischians are a little bit weird among dinosaurs in that they lack those clear signatures of bird-like breathing. They lack pneumatic bones, they lack those big bones.
Were the ornithischians breathing like crocodilians with the hepatic piston?
Something similar, actually. Yeah, and so that's something that we have hypothesized. And this new Heterodontosaurus specimen that I'm working on preserves a suite of new morphologies that really elucidate how that transition happened. They really happen. This new specimen shows that transition.
So Healy's seemingly arbitrary division of ornithischians versus Sauricians or Sorniscians, or
Sauricians, yeah.
However you want to say it. It appears to be valid, but not for reasons he could have guessed.
Yeah, it was a bit of a mess up because the Saurician condition really is the primitive condition for archosaurs to have a forward-pointing pubis. It's a little bit of an arbitrary thing. Ornithischians really are unique. They do something very weird and wonderful with their pelvis, and I get why he separated them. But
you know, this is a family show, right? Kidding. You talk about how ornithischians do something really weird and wonderful.
Oh, my bad.
And we're talking about a pubic bone here.
Yep.
Okay, sorry.
So the ornithischians, they tuck the pubis between their legs. It goes all the way back, and that happens almost instantly as far as evolutionary timescales go. There really isn't an intermediate ornithischian dinosaur.
Well, isn't there
but there is intermediate positions for that pubic bone. That was the deciding factor once upon a time when they said, okay, well, forward, then it goes in this group, and backward it goes in this group, and then they started finding out, I don't remember which species it was, but there was a sequence of species where that bone is moving progressively forward, and so so that it actually exists in both sets.
Yeah. So what ends up happening is that the theropods, interestingly enough, also retrovert their pubis. Their pubis also goes from pointing forward to pointing back. And that happens in alvarezsaurs. They have a backward-pointing pubis. And then things like dromaeosaurs as well, so velociraptor and those guys, they also have a backwards-pointing pubis. Therizinosaurs also evolve a backward-facing pubis, but for slightly different reasons. But there was a paper that came out pretty recently that showed that when the pubis retroverts, when it angles back, it always tends to coincide with a shift in the way that a group breathes or ventilates their lung. It entails a huge overhaul to their body plan and their body musculature and that sort of stuff. So yeah.
So Oran, you were asking us earlier why we got into paleontology, how we got into paleontology, and what I wanted to say was that it's actually because of people like yourself that put out YouTube videos on evolution and paleontology and all of that. And in my case, it was Richard Dawkins about 10 years ago. I used to watch all of his conference presentations, TV interviews, BBC series, and it was literally 2009 when I discovered and really understood evolution properly for the first time. And I found it to be the most interesting subject that there is.
Can you elaborate on how it was that you were in your 20s?
Yeah.
Before you knew what evolution was.
So in South Africa, in primary school and high school, in the 80s and 90s, we weren't taught evolution. It wasn't a word that was printed in the textbooks. And I found out later on that it was excluded from biology textbooks from the 1950s to the early 2000s. So when we got the new government in '94, they updated the curriculum, and now the kids are all taught evolution. They're taught hominid evolution and the record in South Africa, which is very good. But we were literally not taught evolution. It wasn't a thing. So I just discovered it slowly on documentaries, and especially with the rise of the internet and YouTube and all those things. And literally Richard Dawkins, I really, really enjoyed all of his videos. It's a combination of science and biology and evolution, and also atheism and anti-religious talk. And I really, really enjoyed that stuff. And so much so that I discovered that in my late 20s, I was already working at a bank as a business analyst, also called a systems analyst sometimes. And I started volunteering at the university in the cradle of humankind near Johannesburg. And then I met Bruce Rubidge, the head of our department, the one day. And we spoke about doing a one-year degree, which we call an honors degree. It's between bachelor's and master's in South Africa. So I tried to keep my job, but they wouldn't have it. So I had to resign. And I resigned 7 years ago. And I've now done honors, master's, and PhD in vertebrate paleontology. And that's it. Thanks.